Hello, welcome back. Let's talk about theorem 3.9 here. If A is a square matrix, then its determinant is equal to the determinant of its transpose. This is another one that feels pretty weird, especially when you think about volume. Like, for example, if you have these columns in R3, you can make a parallelepiped out of them, and it's going to have whatever volume it has. I don't know. That's the determinant of A, hopefully. But if you get the transpose of that, the columns are now 1, 7, and 0, and 2, 8, 2, and 3, 9, and 0. Why should these columns here make a parallelepiped that has the same volume as these columns? It turns out it works. It's weird, right? But it works. So let's see. To prove it, we're going to do a similar trick as before. I mean, it's not exactly a trick. It seems like a pretty reasonable thing, is break this into a case where we have an invertible matrix or a non-invertible matrix. Because we know the determinants of non-invertible matrices are always 0. And if it is invertible, we can do something with elementary matrices. So first, let's look at the case that if A is not invertible. So if A is not invertible, does that mean A transpose is not invertible? Seems like probably right, but how can we really prove it using theorems that we know for sure? Well, we know that if A is invertible, then A transpose is invertible. But this doesn't really apply to matrices that are not invertible. So the trick is that A is equal to A transpose transpose, right? Turn the rows into columns and then turn those columns back into rows again, and you get A. And if this is not invertible, that means that the conclusion of this theorem is false. So A transpose is not invertible. That means A cannot be invertible. But of course, instead of A here, what I'm really talking about is A transpose. So if a transpose of A transpose is not invertible, that implies A transpose is not invertible. So that was probably confusing because we're both replacing A in this theorem with A transpose and also using the contrapositive of it. That's the contrapositive of part 2 of this theorem, and replacing A with A transpose. So anyways, yeah, A transpose is not invertible, and that means the determinant of A is 0, and if A transpose is not invertible, that's also the determinant of A transpose. And they're equal. Okay, so it works with non-invertible matrices. What if A is invertible? Then we're going to do the same trick as the last time with elementary matrices. So if A is invertible, it's row equivalent to the identity matrix using the invertible matrix theorem. And there's a sequence of row operations that transform A to the identity matrix. But you could also transform the identity matrix back into A by doing the reverse of those row operations. And we know from theorem 2 point something that if we multiply the identity by these elementary matrices on the left, the result will be the result of doing that operation to I. And we do all of them in the right order, we get A as a result. From here, the proof is going to be pretty much the same as with the last theorem, but with a few more difficulties. We'll see. The first thing we can do is the same trick where we apply lemma 3.7 a bunch of times. First, you separate out the determinant of everything up to 2 and E1. Then separate out E2 from that, and eventually you get all these determinants multiplied separately. Now, what about the transpose of A? Well, that's just the determinant of the transpose of the product of all these matrices. And we know the transpose of a product is a product of the transposes separately, but you've got to multiply them in backwards order. So transposes of elementary matrices are still elementary matrices. And so we could still use lemma 3.7 to separate out the first bunch of them from the last one n different times until you have n different determinants multiplied together. And these are almost the same thing as what we had before, just written in backwards order. But of course, determinants are just numbers, so the order they're written in doesn't matter. So to prove the theorem, we just need to show that the determinant of each elementary matrix is equal to the determinant of its transpose. And to do that, we just need to think about the different kinds of row operations that were done from the identity to get this elementary matrix. Like, if it's multiplicity placement, then the elementary matrix that represents multiplicity placement, like for example this one, is equal to the determinant of the identity, because doing one row multiplicity placement is equivalent to just doing a different column multiplicity placement, and that doesn't change the determinant. Another way to think of it is that it's going to definitely have ones along the main diagonal. So those are definitely equal. What if it's a scaling operation? Well, the result of a scaling operation leaves you with an elementary matrix that's symmetrical. It's equal to its transpose. Let's see why that is. Like an example of that is right here. If you take the identity matrix and scale a row, you're only scaling the thing that's on the main diagonal. Everything away from the main diagonal is still 0. So this is equal to its transpose. Like this row is still equal to this column. So of course, the determinant of E is going to be equal to the determinant of E transpose because they're the same matrix. Okay, now the same thing also works for swapping rows. Why that is, that was an exercise that I think is in the 2.4 homework. Maybe we can just see like a quick example of why it works here. So this would be an elementary matrix for a swap. If we swap row 2 with row 5, this is what you get. And you can tell that the transpose of this is still going to be the same thing. So the only thing that's different about these two matrices from the identity matrix is what's right here and right here, 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 and right here. And you can see that the ones are automatically going to be in row 5, column 2, and also in row 2, column 5. So if you get the transpose, that becomes, again, row 5, column 2, and row 2, column 5. So those are the same. So that's a quick explanation for why that works. So either way, whatever kind of operation we're talking about, we have the determinant of any elementary matrix that's the result of doing a row operation to the identity gives you the same thing as the determinant of that transpose, which means every one of the factors of these elementary matrices are all equal, and that means that the determinant of A is equal to the determinant of A transpose. Neat. All right, so in the next video is optional. You can skip it if you want. I just want to talk a little bit about the logical weirdness of what we're doing, defining determinants as signed volume in terms of like the properties that signed volume should have. But you can skip it if you want. What you should not skip is the cofactor expansion in the video after that. And by the way, in that video, you might notice that this theorem is like theorem 3.12. That's because in the middle of making these videos, I realized I needed to rearrange a bunch of the book to make it simpler to understand. So there's like one less theorem than there was before, but I don't want to record that video again just to change that one thing. But yeah, it's the same theorem that's right here. Anyways, I will see you later.